Hello, class. Welcome to the next math lesson. We're still in Module 3. We're very close to the end of Module 3. This is actually Lesson 12. It's the last lesson in the main part of Module 3. We do have a little bit of a short part that we'll work on next after the Module 3 test. But this is the last lesson in the main part of Module 3, Lesson 12, called Modeling with Similarity. And it's in your Module 3 workbooks on page 137 to 147. So make sure you have those workbook pages out and ready. Make sure you have your notebooks or note pages ready to work on, and start copying the notes you see on your screen. Because this is the last lesson in Module 3 proper, what we will be doing is we'll be using all the skills we learned so far in the last half of Module 3 and applying them to real-world situations. We're going to be applying some of the skills we've learned. So we're going to see some real-world problems that we're going to use Similarity to help solve. So the road so far, what have we learned? We've learned about similarity. We've learned how to prove similarity using the AA criterion, using rigid motions, and using scale factor. And we've used how to use similarity to find missing lengths in triangles. So you know what similarity is, you know how to prove it, and you know how to use it to find the missing lengths in triangles. Specifically, we've been focusing a lot on triangles, and we're going to keep doing that today. So today, we're going to apply our skills to some real-world problems. So we're going to take some situations that people actually work with every day to solve some problems, and we're going to show how knowledge of similarity and this list of things right up here is used to solve some problems in the real world. And the first problem we're going to look at actually involves a flagpole, measuring how tall a flagpole is. And can also be used to measure how tall buildings are, how wide things are. These are things where you cannot really use a tape measure, how you can use similar triangles to find the lengths of really big things that are just hard to find in other ways. So hopefully you've copied down those notes. That's the notes for today, because really we're just using the skills. And so the big learning today is how to use the skills in real world problems, how to recognize what skills we need, how to read the problems, and how to understand what we have to do. So hopefully you have your notes written down. If you do not have your notes written down, you can go back and write them down more later. Or you can pause. If you're watching the video right now, you can pause the video, go back and copy the notes. But I'm going to move on, and we're going to get started on our first problem. And I think it's an example problem on page 137. And it's all about a flagpole. So this is our flagpole problem. It says, not all flagpoles are perfectly upright, perpendicular to the ground. That means not every flagpole is straight up and down. Some of them are at angles. Some are oblique, not parallel or at a right angle. They're slanted. So some flagpoles are slanted. So imagine an oblique flagpole in front of an abandoned building. So this is a building there nobody's in, and we have a flagpole in front of it. And they kind of drew it right there. This is a flagpole in front of an old, useless building. The question is, can we use sunlight and shadows? Can we use sunlight and shadows to find the length of the flagpole? So yes, you can. Let's just think about this. Let's say you are in charge of tearing down this building, and there's a flagpole in front of it, and you need to know how long the flagpole is going to be, because when you tear out the flagpole and throw it away, you need to know how big it is to know if you have a big enough truck to carry it. You also need to know how big it is when you take it and recycle it or take it to the garbage dump, because places charge you based on size of things. So we need to figure out how long this is. Can we use sunlight and shadow to do this? And yes, we can. We can use sunlight and shadow to find how long this flagpole is We do not need a tape measure to measure the whole thing. We can just use sunlight and shadow. Let's talk about how. So, assume that we know the following information. The length of the shadow of the flagpole is 15 feet. Okay, so the shadow is 15 feet. Let's draw that. Let's draw the shadow right here. Brown line shadow is going to be 15 feet. There is a mark on the flagpole 3 feet from the base. The base is the bottom. So there's a mark right here, and it is 3 feet from the bottom. So this part is 3 feet, and there's a mark. And then the length of the shadow on the 3-foot portion, so the shorter shadow, this 3-foot section right here makes a shadow right here that is 1.7 feet. So we have that flagpole is 1.7. We have the mark is 3 feet. And we have the shadow is 15 feet. Now, if you look at this, this actually makes 2 triangles. The whole flagpole, the flagpole and the shadow make that triangle right there. And the mark on the flagpole and that shadow and the short shadow makes a triangle about right there. So now we have 2 triangles. We know this is 1.7. We know this is 15. We know this is 3. And what we are looking for, remember, is the length of the whole flagpole, which we don't know. I'm going to call it X. So that is what we have. We have 2 triangles, and we have missing pieces. Now, because this was made by a dilation, we know this triangle, this small triangle gets dilated to be bigger to the whole flagpole. These are similar triangles. These are similar triangles. We can even label them. Let's do A, B, C for the big triangle. And the little triangle is going to be A, B prime, C prime. So we know that A to B prime, that line right here, this green one, is 3 feet. We know A to C prime, this blue one down here, the small shadow, is 1.7 feet. And we know A to C, the big shadow, is 15. What we don't know is AB, the flagpole. That's the unknown, that's X. So can we use what we've learned to find the length of the flagpole? Yes, we can, because we know these triangles are similar. We know these triangles are similar, so what we're going to do is we're going to use the skills that we learned yesterday in our lesson, because we have 2 similar triangles. Triangle ABC is similar to triangle AB prime C prime. And if they are similar, you know that R equals R. So we're going to use this. They are similar, so R has to equal R. The scale factor for one side equals the scale factor for the other side. So we are going to use what we know to find the length of the flagpole. So we need AB. So we need R of AB. That's what we need to know. That part is missing. And so we're going to use R of AC to find it, because we know AC. We know both pieces. And in your notes yesterday, you remember that R is the prime divided by the original. R is the prime divided by the original. That's what R is, based on the dilation equation. Well, R of AB is going to be AB prime divided by AB, because it's prime divided by the original. And R of AC is going to be AC prime divided by the original AC. Now we put in, after we do this, we have a list of our measurements right here, and you can see them on the diagram. So we're going to substitute. AB prime is 3. AB is the missing one, X. AC prime is 1.7. AC, the original, the shadow, is 15. Now we have our equation all filled in. We just need to solve it and find out what X is. What is the flagpole? So how do we solve this? Remember from lesson 11, we cross multiply. Just like you did in your 6th grade math when we're solving ratios, we cross multiply. So we do 3 times 15 equals 1.7 times X. 3 times 15 is 45. So we get 1.7x equals 45. I want the x all by itself, so what I do is I divide by 1.7, because 1.7 divided by 1.7 is just 1, and 1 times x is just x. But if I change this side, I have to change this side, so I have to do 45 divided by 1.7. This is where you are allowed to bust out your calculator and use it to help you. You do 45 divided by 1.7, and you get 26.47. I'm just going to round to 2 decimal places. So we get 26.47. That's how long the flagpole is. Because we compare the ratio of the shadows to the ratio of the flagpole, we can find out that the flagpole is 26.47 feet long. So the flagpole equals 26.47 feet. It's about that. Not exactly, because it was a decimal, but that is our answer. So we used shadows and sunlight to find the length of a flagpole. And that's what we're doing today. We are figuring out what we need to find missing lengths. Just like yesterday when we found missing lengths, we're doing the same thing today. Only instead of just random triangles like yesterday, this is real world stuff. So this is just like lesson 11, only real world problems, real things, and you have to figure out what is missing and what information you need to find it. What I'd like you to do right now is take a little bit of a break, go back, maybe finish your notes if you're not done with your notes. So look back at this example. Make sure you understand what I did and how I did it, and then unpause the video when you're ready to work on a couple more exercises to practice together. Okay, class, you should take a little bit of a break and you checked your notes, you checked your work on this example to make sure you're following along. Now it's time to look at some more exercises. We have 3 exercises we're going to look at. And starting with this one where we are trying to measure the height of a building. Let's read the directions. Number 1, you want to determine the approximate height of one of the tallest buildings in the city. You are told that if you place a mirror some distance from yourself so that you can see the top of the building in the mirror, then you can indirectly measure the height using similar triangles. So if you put a mirror on the ground right here where there's an O, and you stand so you can see the top of the building in the mirror, you can measure the height of a building. This is actually how people measure buildings. They use mirrors and they use similar triangles. So let O be the location of the mirror so that you can see the top of the building. So this is you, little stick figure you. You look down at the mirror and you see the top of the building in the mirror. So you can draw a line from the top of the building to the mirror and from your eyes to the mirror. and you are standing straight up. And we know the angle of these triangles is 36 degrees. So you stand so that the angles match. So we know the angles match right here. We know this is 36 degrees, and we know this is 36 degrees. That's the only information we have right now. Part A is asking us, explain why triangle ABO, this little one, is similar to triangle STO, the big one. Are these similar triangles? And yes, they are, because, well, one, you know, it has one angle that matches. They are similar because we can use the AA criterion. Now, you might be saying right now, Mr. Baylor, the AA criterion tells us we need two angles that match. This is only one. Well, there's another angle that matches. I don't know if you notice it, but if you look over here, next to the building, the big triangle next to the building makes an L shape, which is a right angle, exactly 90 degrees. And if you stand straight up right here, you make another 90-degree angle. So we actually have two angles that are equal. We have a 90-degree angle and we have a 36-degree angle. So angle AOB equals angle SOT, and angle ABO equals angle STO. We have two angles that are equal, so they are similar. AA criterion means they are similar triangles. These are similar. It just got, what happened was, you can see it got, the big triangle got reflected, flipped over, and dilated. It shrunk. So it shrank and flipped over. So these are similar triangles. We know they are similar because the AA criterion. We have the red angle that is equal, and we have the blue 90-degree angle that is equal. We can see that. We know they are similar. And because we know they are similar, we know the scale factor has to be the same. We know R equals R everywhere. So now we can find missing pieces. If they are similar, we know R equals R. So part B, we know they are similar, so now let's label. Label the diagram with the following information. First, the distance from eye level straight down is 5.3. So eye level straight down is this side right here. Eyes, your eyes straight down is 5.3. And then the distance from the person to the mirror, from person to the mirror is 7.2. So right here, BO is 7.2. BO is 7.2. And the third information we know, the distance from the person to the bottom of the building is 1,750. So from the person all the way to the building, this long length right here is 1,750 feet. And the height of the building, the height right here is X. That's how we label everything. So let me show you my labels so that you can see that I labeled everything. We have the 5.3 for this part of the triangle. We have the 7.2 for this part of the triangle. We have 1750 for this, from all the way from the person to the building. And X is the height of the building. There we go. So now we're almost ready to go. Part C, what is the distance from the mirror to the building? So what is the distance from the mirror to the building? So it's first, now it's asking us, what is this one right here from the mirror to the building? Well, for that one, if you look, all we have to do is do this. If we know 1750 is everything, but this little piece is 7.2, then we do 1750 minus 7.2 to find this piece. So 1750 minus 7.2 is going to be 1748.8. I'm sorry, not 48.8. 42.8. Let me fix that. 1742.8. Because 7.2 and 1742.8 makes 1750. Let's check it with the calculator just to be sure. Let's do 7.2 plus 1742.8, and we get 1750. So this piece and this piece makes 1750. So we can write that down right here for part C, 1,742.8 feet is the answer to C. So now we have a lot of things labeled, but what is still missing is the height of the building. We are still missing the height of the building, which I think if I go to page 139, it's going to ask, do you have enough information to determine the height of the building? And yes, we do have enough information to find the height of the building. Let me show you why. If we look, remember R equals R. So I need R equals R. I need two sides that can be compared to each other. Now the first side I'm going to use is down here. I'm going to use the pink side. Because remember, these sides go together. The bottom of the small triangle is connected with the bottom of the big triangle. So these sides go together. Now I also need a side that goes with the building height. Now the building height goes with the person height. Those are connected. So just like yesterday when we found missing pieces, we know these two pieces go together, and we know this piece, and we know this piece is connected. So we can do R equals R. So for this, we need the person height and the person and the building height goes with the person base and the building base. So those are connected. If you see, the person height is connected with the building height, and the person base is connected with the building base right here. Small triangle bottom, big triangle bottom. So what we do, we know the person height is 5.3, because that's how tall the person is right there. The building height is the X, is the missing piece. The person base is the 7.2 right here, the small triangle, and we know the building base, the big triangle, is 1742.8. 1742.8. So now because we know the small triangle pieces and the big triangle pieces, we can use these to find the building height. We're just finding the missing piece. And once again, we do this by cross multiplying. We know these pieces, and the pieces we know help us find the piece that's missing. So let's cross multiply. When we cross multiply, we get 5.3 times 1742.8, and that equals 7.2 times x. Let's do, and this is, I'm going to use my calculator. I'm going to do 1742.8 times 5.3, and I get 9,236.84 equals 7.2x. And you remember I have to divide both sides by 7.2 because that is how we get x by itself. So let me divide this number by 7.2. So we find out the building is 1282.89 with a 4 that goes forever. That is how tall the building is right there. And we solved that by using similar triangles. We solved it by using similar triangles, taking what we know and figuring out what we don't know. So that was a little bit of a fun thing. We can even add it to our box right here. 1282, and I'm just going to say 0.9. I'm going to round to 0.9. And the way we did this, we know they are similar, so we know R equals R. So we know these two change with a scale factor. So the scale factor that changes the pink has to be the same scale factor that changes the green. Pink and green change the same way. So we find how pink changes, and we change the 5.3 the same way. So pink and green both change the same way, and that's what happens when the green changes. We know how the pink changes because we measured it. And we can figure out how the green changes by using ratios and putting the ratios equal together. There is another example that we're going to talk about. Let's look at example 2. And so in example 1, in exercise 1, we measure the height of a building. For number 2, we're talking about measuring how wide a lake is. So how wide is this lake? So this says a geologist wants to determine the distance across the widest part of a nearby lake. So he wants to know the widest part, which is right here. The widest part of the lake is BC right here. The geologist marked specific points around the lake so that the line containing DE would be parallel to the line containing BC. So DE and BC are parallel. We know they are parallel. So I'm going to put them both blue. The line BC is the widest part of the lake, so that's what we're looking for. So I'm going to put an X there because that's what he wants to find. He wants to find the widest part of the lake. The segment DE, he picked DE because he can easily measure it. He can easily measure DE. Now the question is, has the geologist done enough work so far to use similar triangles? So it's asking, do we know these triangles are similar? That's what part A is asking. Is triangle ADE similar to triangle ABC? Is that true? And yes, it is true. You can know this is true. Because if you look, we can figure out that they have the same angles. Because they told you these are parallel, so you know that they have corresponding angles. So this angle right here in ABC and this angle right here in ADE These two angles are equal because they are corresponding angles right here. And because the lines are parallel, these angles are also equal. This angle right here and this angle right here are also corresponding. And we know both triangles share angle A right there. So all the angles are the same because these are parallel lines with corresponding angles. Parallel lines with corresponding angles. We use the AA criterion. AA criterion with corresponding angles shows us that these are similar triangles. So the geologist has made similar triangles. Now all the geologist has to do is measure his similar triangles and use his measurements to find X. So let's look at page 149 and see what he's measured. So the geologist made the following measurements. DE is 5 feet. So let me put that in. DE is 5 feet. AE is 7 feet. So let me do AE right here is 7 feet. EC is 15 feet. So EC is 15 feet. So right here is 15 feet. So does he have enough information to find the widest part of the lake? Is this enough to find the X? Yes, it is. It is enough to find the X. Let me show you why. In fact, it might be easier if we draw the two triangles separately. So let's do the small triangle right here. And let's do the big triangle right here. I moved them away from the diagram and I separated them so you can kind of see them a little bit better. Now the small triangle, you know, is 5 right here because that's the 5. And you know it's 7 right here. You know the big triangle, this is the X that we're looking for. What is this measurement right here? It is not 15. A lot of people might think it's 15. But remember the big triangle right here, this section is 15. This bar is 15. To finish making the triangle, we have to go the whole way back to A. So 15 is only part of the triangle. The whole side is 15 and 7. So this side is 22. So that is the trick to this question. Now we have two similar triangles. We know they are similar because we did part A. And we have a piece we know and a piece with a missing thing. But remember, R equals R. So the blue R, because they are similar, equals the pink R. These are similar triangles. So the blue ratio equals the pink ratio. The blue ratio has to equal the pink ratio, which means we can set up our fraction ratio. So for part B, we know the blue ratio equals the pink ratio. So we can use this information. So I'm going to say the blue ratio is 5 and X. Those are our blue numbers. So we take 5 on top of X, and that equals the pink one, which is going to be 7 on top of 22. So this equals 7 on top of 22. So we can see this, we can measure this, we can solve this ratio now, because you know to solve it, we cross multiply. We cross multiply. So what we do is we get 5 times 22 equals 7 times X. Now, let's finish our work up here. 5 times 22 is 110 equals 7 times x. So to solve this, we divide by 7 because 7 divided by 7 is 1. And that makes x by itself. I also have to do 110 divided by 7, which is probably going to be some kind of decimal answer. So let me use my calculator. 110 divided by 7 gives us about 15.7. I'm just going to round to 15.7. So the widest part of the lake is 15.7 feet. So the widest part of the lake is 15.7 feet. That's our answer. And we did that by using ratios. We did that by using ratios. We took what we know, we measured the small pieces, and we did 2 similar triangles, and we said R equals R so we can find them. We did the ratio equals the ratio so that we can find them. This is what we're doing today. This works when we are measuring how tall a building is. It can work when we're measuring how wide a lake is. But yes, we can do this. Now, there is a part C to this. I'm just going to tell you it. It says, what if he can only measure 12 feet? Could they still find the distance? What do they need to do differently? Well, if she can only measure 12 feet, then what she's going to have to do is move this a lot because this is 15. If she can only measure 12, she'll have to move this one 3 feet closer. So that's what she'd have to do. So what she would have to do is she would move DE 3 feet closer to BC. She would move DE 3 feet closer to BC. That would make her only have to measure 12 feet. Because if this moves 3 feet closer, the 15 turns into a 12, which is what she can measure. The 15 turns into a 12. The 7 turns into a 10. Measuring DE might be a little bit trickier after she moves it, but everything would be smaller than 12 so that it's still possible. If her tape measure only goes up to 12, she can still do it. She just has to move the DE line. So that's what we have. There we go. So hopefully you checked on that. Hopefully you understand how when we know triangles are similar, we can use the R equals R to find missing pieces. We have one more example we want to talk about. This is example 3, exercise 3. It's about a farmer planting a tree that they want to give shade to their house eventually. So this is what we have. A tree is planted in the backyard of a house. Here's our tree right here. I'll color the leaves green. That's our tree right there. And they hope one day it is tall enough to give shade to the whole house. So they want this tree to grow. They want this tree to grow straight up so that it gives shade to the house. Because if the sun hits the tree, then the shadow will cover the whole house. That's what they want. They want a tree that will grow and the shadow will cover the whole house. So what do they need to find the height of the tree? So what information is needed to find how tall the tree has to be to give the shade? So right here, this length right here, this green line, that's the X. What do they need to find the X? What do they need to find how tall the tree has to be? Well, remember, we need similar triangles. We're always talking about similar triangles in this lesson. Well, if we want X, we need to know this bar right here. So I'm going to make another triangle that we can measure right here. If this is X, we need the height of the barn to match with X. Because the height of the tree, remember, we need pieces that line up. We need pieces that will go together. So the height of the tree and the height of the barn have to be known. We need to know the height of the barn. The height of the barn is connected with the height of the tree because that's what we want shade in. Or the height of the house is connected with the height of the barn. I suppose it's a house, not a barn. So height of the barn, height of the house, not the barn. We also need another side that we can measure. We also need another side that we can measure. We need this right here. We need that piece of the triangle. And we need that piece. We need both the blue and the pink line. We need the distance from house to end of shadow. And we need the distance from the tree to the end of the shadow. So if we know that from the house to the shadow and the tree to the shadow and the height of the house, that will give us 3 pieces of information that we can use to find the tree. Now, why do we want these 3 pieces of information? Well, first, we can use a tape measure. It's easy to measure how tall the house is. It's also easy to measure how these things on because they're flat on the ground. We can measure the blue and the pink because those are flat on the ground. So these 3 things are easy to measure. What's going to be tough to measure because the tree isn't grown yet, the tree is still small, the height of the tree is tough to measure. So we use 3 things that are easy to find. We have 3 pieces of information, so we can find the missing 4th piece of information. So let's look at part B. I think in part B, they're going to tell us what these are. So it says the sun has a shadow 32 feet from the point on top of the house to a point in front of the house. So the shadow is 32 feet from the, so this is going to be 32 feet right here. So blue is 32 feet. And it says the distance from the end of the house shadow to the base of the tree is 53 feet. So we have 53 feet right there. And it says the house is 16 feet tall. So this is 16 feet tall right there. Now we can use this to find the tree because we have our 3 pieces of information. And so we know that R equals R. So the R for this house, for the small triangle has to equal the R for the big triangle. We know that R equals R. So let's look at the pieces that go together. 32 and 53 go together. So we take the 32 because R equals R. We know the 32 and the 53 go together because they're both the bottom of the triangles. So we know also the 16 and the X go together because those are the same triangle sides. The 32 and the 53 go on the bottom. The 16 and the X go up and down. So those go together. And we can use this ratio to find X, how tall the tree has to be. We just cross multiply. And we get 32 times X equals 16 times 53. So let's get our calculator and do 16 times 53. And we get 848. And we know that we have to divide by 32 to get x by itself. And when I divide by 32, I get 26.5. So the tree has to be 26.5 feet to make the house in shade. So x is going to, when x is 26.5, that's when the house will have shade. When the tree is 26.5 feet, the whole house will have shade. And we use this by finding the pieces we know to find the piece that's missing. So that's when the tree is 26.5 feet, that's when the shade will be good. But how long is it going to take to be a 26.5-foot tree? Well, let's look at part C. Part C says the tree grows 2.5 feet every year. And the tree is 7 feet tall now. How many years will it take the tree to reach the height? So we want the tree to be 26.5 feet. That's what we want. Now it is 7 feet. How much left is there to grow? So what does it needs to grow? We do 26.5 minus 7. It needs to grow 19.5 feet. So it's at 7 feet. We want 26.5. That means it needs to grow 19.5 more feet. How long will it take to grow 19.5 feet? Well, it grows 2.5 feet every year. So how many years to go 19.5? Now you can do this by repeated adding, where you do 2.5 plus 2.5 plus 2.5 plus 2.5 until you get to 19.5. Or we can just divide. We do 19.5 feet divided by 2.5 every year. So if we take 19.5 and divide by 2.5, we find out that it's going to take 7.8 years for the tree to finish growing. 7.8 years. You can say about 8 years for the tree to get tall enough. So it's about 8 years for the tree to grow to give shade to the house. So this is what people actually do. When people want to figure out how tall a tree has to be, they can use similar triangles to figure that problem out. Because you can, and that will tell you how many years away until you get your shade. It'll tell you where the shade's going to be. It'll tell you how long you have to wait. So similar triangles can help us find missing information that is hard to measure. Like in exercise 1, it is hard to measure how tall a building is, but we can use similar triangles to help. In exercise 2, it's tough to measure how wide a lake is, but similar triangles can help. In exercise 3, it is tough to know the future and how tall a tree has to be, because it's hard to tell the future. But you can use similar triangles to make guesses, to make hypotheses about the future. Those are the 3 exercises. I'm going to take a little bit of a break, pause your video, and think about these exercises. Think about if you have any questions about these exercises. Send me an email if you have any questions. If you understand the exercise and you know what you're doing, then you can unpause the video and I will explain the problem set and the exit ticket next. Okay, thank you for taking a minute to look at those exercises again, double checking your work, making sure you understand everything. Let's talk about your next steps, your independent work. That's the exit ticket. We'll talk about that at the end. Here's the homework helper. So if you need another example to look at, the homework helper will be great because you're using it to find out how tall a statue is. using similar triangles to find out how tall a statue is. So they tell you the question, they give you the answer, and they even tell you what they were thinking when they found the answer. So use the homework helper. It's a good tool. On your problem set on page 147, we're talking about, number one is talking about the world's tallest tree, which is actually right here at home in California. It's about 370 feet tall. In a local park, there is another very tall tree, and you want to find out if the tree in the park is anywhere close to the height of the famous tallest tree. So first, you stand right here and you make some similar triangles. You have a small triangle that is between you and a point on the ground, and you have a big triangle that measures to the top of the tree. So you made two. First of all, you need to tell me, how do you know that these triangles are similar? You're probably going to use the AA criterion, but tell me which angles you know. And then it tells you you have a friend standing in the shadow of the tree, tells you how tall your friend is, tells you how big his shadow is. And then you have to tell me if that is enough information to find the height of the park tree. Then for part C, they tell you how far away your friend is from the tree. And you have to figure out how many feet the tallest tree is compared to your local tree. So you are going to use similar triangles to find out how tall this tree is and compare it with the tall redwood. Now, there's not a whole lot of space on this paper, so you're probably going to do your work on a separate piece of paper, but you should still use this diagram to label the information you have. The second question on the problem set, you're actually going to use similar triangles for a skateboard ramp. You're going to talk about how to build a skateboard ramp. So what they want you to do is they tell you about a basic skateboard ramp that is about 4.7 feet of wood from the ground to the top of the 2-foot ramp. So they make a 2-foot ramp. But what happens if you want to make, instead of a 2-foot ramp, a 5-foot ramp? So this is if you ever thought about building anything or you ever thought about construction, this is talking about making a bigger ramp. You want to make the same angle, you want to make it safe, you just want to make it bigger. So this is, you're going to draw the small ramp, draw the big ramp, and use the measurements to tell me how much wood you're going to use for your big ramp. After you do the problem set, you have the exit ticket, which is figuring out how, using similar triangles to figure out how high a kite is flying. So they tell you how much string they have, they tell you the height of your friend, and you have to figure out how high up is the kite. Distance from the ground to the kite using similar triangles. Go back, use the exercise we talked about today. Use your knowledge about similarity. Remember, after you know triangles are similar, use the R equals R strategy. All the work today is the R equals R strategy, which you know how to do from lesson 11, which I showed you how to do more today. Just use your R equals R strategy to find all the missing pieces that they're asking for. Have fun with it. Remember to use your diagrams. Also remember to ask me for help if you need any help at all. I'll see you for the next lesson. Have a great day.